Hello, my name is Domingues, and this is Lab 4, the magnetic field of a bar magnet. So first of all, this lab is an observation and comparison between two differing models and calculations for the magnetic field of a strong bar magnet. This experiment would not be possible if not for the Biot-Savart law. Biot-Savart law takes into account moving particles and gives an expression to derive the strength and direction of a magnetic field caused by said point particle. My hypothesis for this lab is that the experimental version will remain similar but not completely wrong to the coding version. We also have this special version that we use for the lab, which is the magnetic field due to a bar magnet, which is K times R to the n. So what's actually happening for a physical experiment, we first downloaded magnetometer apps to our phones, so we can locate the magnetometer to the phone and get data. Then we measure the magnetic field on the on and off axis at a bunch of different locations with a bunch of different magnitudes. Then using GlowScript, we simulated the same situation and created a bar magnet and just drew its magnetic field. So here's the real model. We have tape marking where our magnetometer inside the phone is exactly, and then we drew the magnet along using a meter stick to know what our R value would be. Here's the code. You can see us drawing the magnetic field around the in the just all the arrows. So here's how we did the computational model. First, we set up some initial conditions. We have our mu naught over 4 pi. We have our mu magnitude, which we calculate by taking the values from the next slides, which you'll see here. And then we make a function. We define it for the dipole, the magnetic field. And then we also use our observation locations at many different points. So here's us creating vectors for all of our different observation points. And we're using that distance variable. And we can change that distance variable to see what our values are at farther or closer away. And then we had to create a field at an angle. So that's what this last part is. Basically, we created another observation point, and then we did the same exact thing. So here's all of the data from our physical experiment of measuring the magnetic field strength and the distances away. Here is the natural log of B sub x, which is the magnetic field in the x directions versus the natural log of the x distance between the magnetometer and the magnet. It sort of draws a line with the slope negative 2.2263. So the system here, and that value will be n, and we can talk about n again if we go all the way back to up here. We can see our magnitude of magnetic field is k r to the n, and that's that n value is our slope. So what's actually going on? The system is our magnetometer, and our surroundings are the bar magnet. And in our in our coding, we don't really have a system of surroundings because we're kind of just drawing. I guess our surroundings could be the bar magnet, and our system could be each and every one of our observation locations. So our magnetic dipole moment was 38.21, which was slightly different from what we expected, but it was relatively close. Our off-axis value experimental was 3.9 times 10 to the negative 5, and our off-axis value computation was 6.8, the magnitude, which was quite different. There are many possible sources of error, like bad equipment or nearby objects with magnetic fields, but that's just how it is. So lab questions. What if you hadn't oriented perfectly with the Earth magnitude, or with the Earth's magnetic field? So any small change in the x or y would have led to a large impact in comparison with the original reading, which we saw just happening with our normal experiment too. Every time we move the bar magnet 1 centimeter left, 1 centimeter, we had huge changes, and it wasn't even like it wouldn't always return to the same values even. The z portion of the magnetic field will likely not change because we measured everything on a flat surface. So this would always be we wouldn't be worried about it because we were only measuring data in 2 dimensions. So what if you were to stick 2 identical magnets end to end and run the experiment again? Any small change to the length of the bar magnet will increase or decrease the magnitude and length of the field. If it retains its shape, just larger, only the adjusted parts must be adjusted from the previous examples. So basically, we think it would it would obviously change our observation locations and their values because there would be many different values. And then if we had to put sort of a bunch of infinitesimally small bar magnets on top of each other, we could then calculate a long wire of bar magnets. And that's all. Thank you.